Yes. In this class, we will discuss about the torsion of thin wall tubes. So it is also a case of non-circular sections. So sometimes torsion is applied on thin walled sections like this. These are some of the examples. You can have a T section type or channel section type or circular with a hole here or I section type. When these types of sections are subjected to torsion, how to calculate the angle of twist or you can the polar moment of inertia and what amount of torque that particular type of section can take given the value of shear stress. So that maximum shear stress value depends on the type of the material. So in this lecture, I am going to explain you how to compute the polar moment of inertia, torque that can be carried by those type of sections, and also what is the angle of twist that can be developed per unit length of that tube given maximum shear stress. That means for a given material, how to calculate all these things. So this is a comparative type of problem. So I have taken one T section type, one channel section, one circular and another one I section. All the dimensions are given in millimeters. You can see that. So only thing is you have to remember these three important formulas here. So the polar moment of inertia J for these types of sections, that is thin walled sections, is given by this formula: sigma or summation Bi cube divided by 3, where I is the number of rectangles that can be taken from that particular section. For example, here T section you have 2 rectangles, in the channel section you have 3 rectangles, here also you have 3 rectangles. That I represent the number of rectangles. And next to formula to find the torque is given the toe max. So once again I told you that the toe max depends on the type of the material, 150 MPa, 200 MPa, like that they will give. So toe max into J divided by T max. T max is the maximum thickness. So each this rectangular tube, they may have those tubes. Not only they may have this value of thickness different. It may be same or it may be different. So maximum thickness you have to take here, and this will be in Newton millimeter. And finally, you can calculate the angle of twist that the tube can take due to the effect of the torsion by this formula T by Gj. So once again, the G value also will be given. Modulus of rigidity of the material will be given. So in this problem, toe max is given and G is given, and these different types of cross sections are given. So we have to compute J, T and theta. So J is the polar moment of inertia of the particular section, T is the torque that can be developed, and theta is the angle of twist per unit length. For these 4 types of sections we have to find out. Of course, they have given this toe max at 150 MPa or Newton per millimeter square, and G, modulus of rigidity of that material, as 80 GPa or 80 into 10 power 3 MPa. So MPa is Newton per millimeter square. So 1 GPa is 10 power 3 MPa. So these 2 values are given. So we have to compute these 3. Now one by one we will see how we can find out. So first I will take this T section type. So here the formula is for finding the polar moment of inertia is summation Bi cube by 3. So this T section can be split into 2 rectangles. So wherein for the first rectangle B is 100, T is 5. For the second rectangle B is 100, T is 3. Please note that thickness may vary. In this problem thickness is varying. So Bi cube by 3 means for the first rectangle it is 100 into 5 cube divided by 3, plus for the second rectangle it is 100 into 3 cube divided by 3. Okay, that's what I have substituted here. You will get 5066 millimeter power 4. That is the unit of polar moment of inertia. Then T is given by toe max into J divided by T max. So toe max we have that is J value we have got 5066 into toe max is 150 MPa Newton per meter square is given, divided by T max is maximum of these 2. So 5 and 3 are given, therefore 5 is maximum, divided by 5. So you are going to get this much. This will be in Newton millimeter because it is torque. Next, we can find out the angle of twist using this formula T by Gj. So here this is T, whatever you have got, you can write 151,980 divided by G is 80 into 10 power 3. Please note that here you have to substitute in Newton per mm square. So all the units I have kept in Newton and millimeter. That is very important. So you cannot put in different units. So you have to keep it into same unit. I have taken all the units to Newton and millimeter. So this is what into this value of J you got as 5066. So if you substitute and simplify, you are going to get the value of theta in radian. Please note that angle of twist will be in radian. So here you have got 0.000375 radian per millimeter length of the tube. So that is the angle of twist the tube can take. So lesser the twist, stronger is the material, or stronger is the tube. So that is the main. So I think it is a comparative type of problem. In the first case, this type of tube can have an angle of twist of 0.30375 radian per mm. Next, coming to the second type, that is a channel section type or C section we can say. So same formula for J, BITA cube by 3. Here there are 3 rectangular sections, 100 into 5 cube. Thickness is 5 here, divided by 3. Plus here the length is length is 75, width you can say. Into thickness is 3, so 75 into 3 cube by 3. Plus here 100 into 5 cube by 3. So that's what. Summation means you have to add all the 3. You are going to get 9008 millimeter power 4. And torque, corresponding torque will be this formula J into T max by tau max by T max. So J is this 10,008. Tau max can be 150 divided by T max is 5. So 553. So among those the highest is 5. So divided by 5. So you are going to get this value of 270 240 Newton mm as the torque. And theta is given by T divided by Gj. Once again T is this divided by G is 80 into 10 power 3 into J is this. So if you simplify this, you will get same value you are getting 0.000375 radian. That is the angle of twist per millimeter length of the tube. Next, coming to the third, it is a circular type, but one hole is there. So there is a hole here. So what you have to do is, in this case, if you are using this formula, BITA, B becomes the circumference. Please note that B becomes the circumference. Here the total circumference, actually circumference is 2 pi r. Radius is given as 50 mm, thickness is given as 3 mm, this gap is 5 mm. So total circumference is 2 pi r. In that we have to subtract this gap. So your total length of this circumference will be 2 pi r minus 5. So that's what I have taken here. This is 2 pi r. This is r. 2 pi r minus 5 is the value of B into T cube. T is same 3 mm throughout, 3 cube divided by 3. So same formula, but B is circumference here. From the total circumference, you have to deduct this 5 because there is a gap there. Clearance is given. So if you simplify this, you get 2782. Point something you are going to get that I am not writing here. So then T is equal to same formula tau max J by T max. So this is tau max 150. This is J 2782 divided by T max is once again 3 only. Here uniform thickness 3 only. Answer is 139100 Newton mm. Now theta formula is T by Gj. So T is this 139100 divided by G is 80 into 10 cube into J is 2782. If you simplify this, you are getting 0.000625 radian per mm. So slightly higher value you are getting here. Okay, compared to this, you are getting higher value. Next, lastly, fourth one, this high type of section, there are 3 rectangles here. 100 into 5 cube by 3 plus 100 into 3 cube by 3 plus 100 into 5 cube by 3. See, so that's what. So that is your J value 9233 millimeter power 4, and T value once again it is J into tau max by T max. So this is J into tau max divided by T max is 5 here. Among this 5, 3 and 5, highest is 5. So here this is what you are going to get 276 990 Newton mm is the torque, and theta is given by T by Gj. So this is T 276 990 divided by G is 80 into 10 cube into J is 9233. If you simplify this, you are getting 0.30375 radian per millimeter. Now if you observe all these 4, this first one and second one and fourth one. We can comment that all these three, they have the same values of theta. You can see. So irrespective of the cross section, your twisting of all the three tubes, first, second and fourth, they are same. And the third one, we are getting slightly higher value. That means third, the circular type tube is not so much stiff, you can say, or you can, it doesn't have not much torsional stiffness. Okay, so it is when the angle of twist is more, when the angle of twist is more, what you can say that it is not taking care of the torsion much. That is the meaning. So it is not resisting the torsion much. In other words, if your T value is less, torsion carrying capacity or torque value is less, then also your theta will be less. So this theta is directly proportional to T. We can observe that when theta is less, so when T is less, theta also will be less. So T gives an idea of the torsion carrying capacity of a particular tubular section. So in this example, this third section, that is central type of section, this is giving a lesser value of torsion stiffness, or torsion carrying capacity is less, or angular, what you can say, angular stiffness, that what you are getting, it is more here. So it is twisted more. So this is what I wanted to explain you. So this is a comparative type of problem where we have compared the values of polar moment of inertia, torsion carrying capacity and torque, and the angle of twist for four types of thin walled tubes. Okay. So next class I will be dealing with multi-celled tubes, wherein in a multi-celled tubes they are subjected to torsion. How to calculate the shear stress and all.